Hello, everybody. Welcome. Thank you for joining me. Good to have you here. Feel free to say hi in the chat. And as always, if you're new here, please let us know where you're joining us from. Chris, good to see you. Javier, welcome back. Glad to have you here. I'm back from my secret mission. I can now tell you what it was. So I was inducted as a fellow of the American Institute for Medical and Biological Engineering. That's a mouthful, but so that was a really good time, a great honor. And I was inducted around somewhat of, I think it was somewhat for building new academic programs at Carnegie Mellon, but I think largely it was around a lot of the stuff I've had an opportunity to do in online education like Rosalind or our bioinformatics algorithms projects and so forth. So it was a great honor to be a part of that. Stewart is hard to impress here, but largely otherwise, yeah, it was a wonderful time. And I even got a chance to head over to the Capitol. So part of what the organization does is advocates for science in the U.S. federal government. So that was cool to get a chance to do. We got a chance to go over and meet with the staff of our senator in the U.S. So I'd never had a chance, obviously, to do something like that. I probably won't again. But it was really good to talk about making sure that we're attracting people to the U.S. and inspiring them with our training, but also that we're providing the funding that we need in order to stay competitive. So I think it was all a really good time. Got to meet some new potential colleagues and so forth. But yeah, thank you for all the kind words. I appreciate it in the chat. And that's why we didn't have a stream last week, because I was trying to get some more funding for science in America. But I actually have a warm-up question. I got a few questions really before we get into the meat of what we want to do tonight with parallel programming. And my warm-up chat question for you is there anything you do where you feel, and this could be this could be an ability, it could be a weird trait, something like that. Is there any aspect or thing that you do where you feel like you're the only person in the world who does that? As random and as odd as it might be, is there anything you feel like you're uniquely doing, you've uniquely done? Valerie, welcome from Atlanta. Good to have you here. I think I have one thing, which is why I'm asking. It's not meant to be a brag, but I think there's got to be something we all do uniquely. Unique cartooning style. Okay, good. Unique research projects. Good. Sure. Yeah, if you're working on some aspect of research, there's a good chance that in some area you're like the world's foremost expert, because there's so many avenues you can go down, right? I don't know if was ever able to say that one during my research days, but yeah. So mine, which is, I don't know. I remember at the time I was thinking, I think this is my one global thing. Is I've taught programming for 10 years, and I'm sure that the circumstances are different now. This is no longer the case, but I'm pretty sure. And I'm willing to be correct, to stand corrected, and then there will be zero things that I know I'm unique for. But I'm pretty sure that I was the first person anywhere who had real parallel programming in an introductory programming course at that time. Things are going to be different now. Nevertheless, I think having parallel programming as part of an introduction to programming is very important for a few reasons. One of the most, I think, relevant reasons for that is that a lot of the algorithms that are changing the world through AI, they're all inherently parallel, and they run on computers that are inherently parallel. So learning about what parallel programming means, from my perspective, is really important, especially if you take one programming course ever. If you're going to do an entire degree in computer science, then sure, you're going to see this topic. You may take an entire course in parallel programming and algorithms, which is something that our students at Carnegie Mellon do. But if you're just taking an introductory course, that most people who program probably don't go very far beyond that. And so it's important to see parallel programming in my mind, because it has become ever more important in the 10 years since I started introducing it into an introductory class. But that gives me a question for you, which is, what is parallel programming? Do we know? How would you define it? Tell me in the chat. My mom is being very humble in the chat and saying she can't think of anything. I probably could think of 30 things that make my mom globally unique in like an hour. I would say she's probably the only living person to have sat on Elvis Presley's lap. That there's a chance that that's the case, or one of a very small number of people. Roy says multiple threads. Okay, hang on to that thought. Looking for more ideas. Now it says running code on multiple processors at the same time. Okay. I'm also thinking about the notion of parallelism. That's a mouthful, but there's a concept here called parallelism that I think is more broad than just programming a computer. Yasmin has a good term here, which is simultaneously. I think simultaneously is a vital adverb to use when we talk about parallelism. Yes. And how I would say what we have to have is a division of a task or collection of tasks over multiple workers, whatever that means. I mean, I actually think, it's mulch season in Pittsburgh. So if I have multiple people to help me, which I don't, you can imagine we could parallelize the work of actually laying and spreading it out over multiple people. So we have one task that we're working on, and then it's divided out over multiple workers. And if this has very natural connections in programming. For example, if you've used, we'll take a broad view of programming here. If you've used AI, a platform like Claude that has local agents, and it tells you I have 7 or 8 local agents running. This is parallelism. The idea of you gave me a task, I actually can split this up into pieces, and I can make all these individual worker agents help out with completing the tasks. Supercomputers are inherently parallel too. So what makes supercomputers super is that not that the computer is that much more powerful on its own necessarily, as much as the idea is that we have many different cores or machines that are all working on some component of a problem and trying to coordinate this process in some way. And all that is important because it's not just supercomputers, it's not just AI. Computing as a whole gets more parallel each day. I will show you what I mean by that here shortly. And the reason why is that for a very long time, we tried to make computers faster and faster and faster. And that effort has seen a lot of the returns diminish. But what hasn't really diminished is the ability to make computers smaller, more compact, and to manufacture them more cheaply. And so if you're slowing down how much each individual machine can do, but you're growing the total number of machines, then this makes the notion of splitting a task over multiple machines that much more relevant than it ever was to begin with. So Yasmin, I think you had a question. Can we say that AI agents are parallel programming? In a sense, it's certainly parallelism. I mean, I think it's depending on what task you're giving them. There could be code involved, or it could simply be, reading through files on your computer and trying to find something, which, is the computer doing something, but the paradigm is still there. So far the chat has done well. Let me ask you a second question, which is, what is concurrency? There's another term that we often use kind of in the same breath as parallelism, and it's concurrency. Does anybody know what that means? No from BZ's very honest answer. No. But I do think it's reasonable in the sense that probably not that many people who have a good sense of what parallel programming or parallelism means are going to have a good sense of concurrency. And Roy had said something about threads. Nada says multi-threaded, and this is we're getting at this. So we're not going to formally talk about threads, but if you know what threads are, I think that's going to be a good model for what we're going to talk about. I'm going to save a definition of concurrency for when we can see it a little bit in terms of actually putting this into Python. And a lot of people think that it's a synonym for parallelism. Val, thank you for pointing that out. It's not. So there is a Venn diagram, and a lot of times they will intersect. But in theory, you can have concurrency without parallelism, not just in theory and practice. You can have concurrency that's not parallelism. You can have parallelism that's not concurrency. We're going to talk more about the former than the latter, but you'll see I'll talk about an example of something that is concurrent, but that's not parallel. And that sounds like really fancy stuff. My goal is to try and make this seem straightforward to you by giving you some analogies that make it easy to understand precisely what the difference is between the two. So we're nearly ready to start. The purpose of this chapter is to build a parallel simulation for a scientific example. And we're going to get to that. This stream is going to be all about fundamentals. So we will need to, as we've seen so many times, we've made enormous advances, and we've kind of made the leap into object-oriented programming. We should feel very comfortable with that. That's going to come up tonight as well. But this gives us the opportunity to step back again and go through some basics. But before we quite get to that, I did want to ask one more question, which is, what kinds of problems would you consider it? Do you think it would be easy to parallelize, meaning convert to the paradigm of, if I gave you 100 computers instead of just one, and even if we haven't started writing code yet, what are the types of problems that you would imagine having access to 100 computers instead of one would be natural to solve? Where it says protein folding. I think that's a good answer, but I would imagine if I give you a protein folding algorithm to fold a protein on one computer, if I give you 100, if you're folding one protein, I'm not sure that it's obvious, like how that's going to be helpful to have 100 computers all working on trying to fold this protein together. You have 100 hands in there grabbing each other. So that will be a little bit challenging, certainly possible. But if I gave you 100 proteins to fold, well, in that particular case, you could just run the same algorithm on 100 computers and give each one task. So it depends on how we frame it. Yeah, Krish says bioinformatics programs, that's fantastic. So from the same type of perspective, if I'm like, hey, we've got an algorithm and I want to run it on a database of things, like hunt through a bunch of genomes for certain motifs. Well, if I give you 100 computers, you can just divide the work of 1,000 genomes, 10 per machine, and then this is a very natural algorithm to parallelize. Absolutely. Roy, you were thinking of folding at home. Yeah, that's good. And those algorithms are like converting them to parallel is a clever idea. I think there's a little more to it than something like, well, I want to run this algorithm on 1,000 genomes. You take 10, I'll take 10, and we hand 10 to each of 100 different machines. Cool. Alignment is another good example, Javier. I like that. If we're trying to align, say, many things, like I have many fragments of DNA and I want to align them against a database, okay, split up the fragments into a lot of pieces. There's a couple examples that I would imagine. One would be like updating an array. And if you imagine, for example, rendering this stream. If I had 16 computers, I could just divide the screen into 16 approximately equally sized rectangles, and each one would have responsibility for one of those rectangles. This is the foundational idea behind GPUs. They've been applied in a lot of different contexts, but I think it's the most natural way to kind of introduce what is it that GPUs were really kind of initially designed for. They've been very helpful with AI, but the idea was with graphics, if I have a processing unit that's inherently parallel and built for graphics, it makes sense to just split the screen up into a bunch of different pieces. The other example that comes to mind is anything Monte Carlo simulation. So if I want to run 1 million trials and we have 10 machines, just give each machine 100,000 trials and then come back and talk to each other at the end. And that's an example that we're going to see soon. So we're going to build a particle simulator as our big demo. And before we do that, we're going to go back to the foundations of the course and work with a Monte Carlo simulation algorithm and convert it to a parallel paradigm in this way, right? I want to run 1 million simulations. I have 10 cores. Let's give each core 100,000 trials, and then they're all going to come back and report what they've done. But before we get to any of that, I want to do an even simpler example that's going to take us even earlier in our course. And that simple example might surprise you, that it's going to consume an entire stream. But what we're going to look at is summing the values of a list or an array. And this is something that, in terms of how I've brainwashed you to program, is a very simple task. On one hand, I could write a for loop, range over all the elements in a list, and add each one into a sum variable that I declare. So this is just a few lines of code. On the other hand, it's actually built into Python, so you don't even have to do that. You can just call sum of the list. What we're going to see is it will occupy all of our work here, is truly understanding how I would take the reasonably simple task of summing the elements of a list and split it over a bunch of different processors. On the way, even though it's a simple example, we're going to see we have plenty to learn, and that's going to help inform coming back and doing a Monte Carlo simulation or coming back and doing a scientific simulation. Okay, so we're about ready to start. As always, please like and subscribe. It helps us stay visible. Send us a super chat. I tried to get us a super thanks goal of $420 today, but it didn't work out. Join our Discord and email to stay in touch with us and hear about everything that we're doing. And we're ready to start. So let's code. You can see I've got some starter code here, but we don't have very much at all. Get rid of my self-indulgent photos. To get started, you'll see I have a parallel folder in our Python src directory, and I just have a little bit of starter code in main. So everything that we're going to do here is really just going to require one module. And that module is going to be imported at the top, and it's called multiprocessing. It is a notoriously slow, unpopular, maybe even hated Python module. We'll say a lot more about that later, or a little more at least. But before I get into my Python frustrations, the first question we're going to ask is a very natural one that you might ask about your computer. And that question is, how many computers does this computer have available? I think probably I should say a better term would be core. So for a long time, when you were sold a computer, it had one CPU. That was certainly the case when I was a kid, for example. And even I think the laptop that I took to college had one CPU. It was a powerful CPU for the time, but one CPU. And then as the paradigm of parallelism has taken hold, one of the things that happened in around the aughts is that computers started being sold with more than one core as a standard. And this was helpful because if you have a couple of cores, in theory, you could have twice the applications open on your computer. So you could handle a larger load. And this addressed the fact that with a lot of things, we were unable to continue getting performance improvements at the rate that we had seen. But as the cost of making those CPUs came down, it just made sense to make them smaller and put them into the same place. So I can very quickly access this by calling multiprocessing, and then calling this CPU count function. So I'll run this code just so I can see, and I would say let's make sure that we navigate into src parallel, and I'm going to run with Python 3 or Python on a Windows machine, main.py. And this a lot of times it's a power of 2, but this particular computer that I'm showing you this on has 10 cores available. What number do you get? So tell me in the chat. I'd be impressed if you get 10, but if you run this, what's the number of cores that you get? I should also say, this paradigm is what allows for this sort of thing to happen, that I've got multiple applications open. We're streaming this. I'm going to be able to run code from a language, and all of that is just kind of naturally handled. And a lot of that is because I have 10 computers living inside my Mac. 9 is an amazing answer. I don't know if I've ever seen anyone have 9. Don't tell me that you mistyped it. Yeah, 12, 14, 16, 8. These are standard numbers. You reach a point where if you tried to pack 128 in a laptop or something, you're not really going to see that many more improvements. I mean, how many applications do you really want to have open at once? But yeah, these days it's typical to see 8 to 16. Good. So I use that as an example of saying your computer is already inherently parallel. If you have 8, 12, 14, 9, 16 cores on your computer, however many you have, it's already doing things in parallel by taking the brunt of its work and dividing it over all of these different cores. And there's a symphony behind the scenes that we're not going to really get into here. And we're fortunate to have, operating systems that handle this for us. But it's good to know that, everybody's computer is inherently parallel. Next, I just want to go through a very simple example of summing the values in a list in parallel. And I'm going to do it for just 2 processes. So I'm not using the term processor because this machine has 10 cores available. Yours is going to have a different number. But I am going to talk about the term process where I'm thinking about dividing the work of summing the values of a list over two workers. So I'm going to have a function called sum example 2procs. It's not going to take any inputs. It's not going to return anything. And what it's going to do is simply walk through a demo for us. So I'm not even going to give it a doc string. What I'm going to take us back to is our old Gauss example of summing all of the positive integers between 1 and n. And let's, I'll say let's split the work of summing the first n positive integers over two processes. So let's get some data first. In the case of Gauss, this was the first 100 positive integers. So we're going to set n equal to 100. And then I'm going to declare my data. The data that I care about is going to be a list, but I'm going to create a list from the values between 1 and not including n plus 1. So now our list is 1 up to n. And that's good. So in the old days, we could print sum of data. And I can write this, run this with calling sum example 2procs, and you'll see 5,050. That's our magic number for the sum of the first n positive integers, first 100 positive integers. But that's not the way we're going to do it. What I'm going to do is I'm going to split my work over two workers. So to do that, let's set the midpoint. Say, what is the midpoint? Well, it's equal to the length of my data, which is just n, divided by 2. And here's a great opportunity for us to do an integer division. So it'll round it down if need be. So if this were 101, it would round it to 50. And then what I can say is, let's make a list containing slices of my original data list. So I'm going to split it up into two pieces. And I'll say, these halves need to be approximately equal size. So our data slices is going to be a list, and it contains two things. It contains the data list of everything up to the midpoint, and then we're going to look at everything from the midpoint onward. Remember, we're not going to include mid here, and we will include it there, so this is another nice benefit of not including the element in the second index when you do a sublist. So this is the prefix, and this is the suffix of data. They're of approximately equal size. And now that I've split this data into two pieces, then the question becomes, what do we do? So what we do is we create a fancy list called a queue to collect the results of the two processes that we will run. A queue is like a list. I want you to think about it as a list, but it has like a little bit of extra safety built in to handle the fact that we're going to be using parallel programming around it. So I won't take that detour to explain that in depth, but it won't quite work if we just use a list. We need to use this special queue. Fortunately, this is going to be an object that just comes in from the multiprocessing module. So I'm going to call the resulting queue, result queue, funnily enough, and then I'm going to say multiprocessing.queue, and this will give me essentially an empty list. So this is a queue object. We haven't put anything into it, but the idea is that this is going to be used by our workers to indicate when they're finished. So when we send our two workers out, and we're going to hand our workers two different pieces, two different halves of the list, each one is not going to see the other's half, and then they're going to perform the summing. And then when they do that, they're going to place their answer into the queue. And then we will grab it from this queue so we can see it. Oh, this worker's done. Thank you for your job. And now once I've done that, I just need to grab twice from the queue and then say, oh, I've got 2 values. I need to add them. So the question becomes, how is it that I do this? The overarching idea is we've seen this idea of using a minion to help us, deferring to something throughout the course, right? We've seen it in the context of subroutines. We've seen it more recently in the context of functions that we're calling recursively, with the idea being I'm delaying having to worry about something, right? Or I'm handing off a chunk of the task to some other process. In the case of a subroutine, that's just a function where our dirty details live. In the case of recursion, the idea was maybe you split this into 2 pieces and then each of those 2 pieces is half as difficult. Or maybe you just take one element off. That's what we saw in the case of summing. I said, I'm going to remember the number n, and then my worker is going to sum the first n minus 1 positive integers, and that wasn't very fair. So in that particular case, the worker called another worker to say, we're going to sum the first n minus 2, and I'm going to remember n minus 1, and that process continued. So this way of thinking about what we're doing, I think, is actually really useful for extending this to parallel programming. And so what we need to do is, create these workers. So I'm going to say we're going to create the minion processes or workers. And they're going to take 2 inputs. So this is always going to be the case. Number 1 is the function name, and that's called target. And number 2 is the arguments, not 2k. Number 2 is the arguments or parameters, which are going to be called args, that get passed into the function. And the function that I mean here is, this is the worker function. So all this function is going to do is sum the values of a list. So I'm going to call that function partial sum. And there's another critical point here, which is that the arguments, well, you think, what does the worker need to know? It needs to know it's half of the list. Okay, good. But it's also going to need the queue, because when it's finished, it's going to place its value into the queue so that then we can see it. So this might sound very fancy. I'm going to show you that this will be the case for any kind of parallel program that we write. I'm going to create processes. So in this case, how many processes do I create? 2. So P0 is going to say multiprocessing dot capital P process. And I need to specify the target, and I need to specify the args. Okay. The args are always going to be a tuple. So when I do this, I'm going to go ahead and place them in parentheses. It would be easy to forget that, but so when we call this, this is our first worker, and we need to say, all right, what is the first worker going to do? The target is the function name. I'm going to call that partial sum. Have we written it yet? No. So Python will get angry at us, and that's fine. We're going to write it here in a second. And then the arguments that it needs are going to be 2 things. So it needs to know which set of the data it's looking at, which in this case is just data slices of 0. So this part of the data. And I mean, I could have just given it data prefix up to mid and not even declared data slices, but I think this is nice coding practice. And then the other thing it needs access to is the result queue itself. So this is how it's going to be able to communicate back to us. And the reason why for that is returning values is going to be very, very challenging to try and understand. So for example, if we start running our code and then I say, oh, this worker needs to go and run this function and then return a value, the problem becomes, well, how do I know when it's done? Like, I want to carry on. Meanwhile, right, if I call this worker, I want to carry on with my part and then maybe call another worker. And the problem with returning values is that's an inherently serial way of programming. It's serial meaning everything is sequential. And up until this point in this course, I've very much brainwashed you to think about all of programming as sequential. So I could give you a huge program. And if I gave you long enough, I could say, well, what are the lines that you execute in this program? You would go to main and you would start executing lines. And every time you saw a function, you would just go to that function. And if you saw a function inside that function, you'd go to that function and you write down the sequence of steps. If you had a for loop, you could write down all of the ranging through the for loop. This would be a nightmare for a big project, but of course you could do it. When it comes to parallel programming, we start to lose that control. Sequential or serial programming is all about always having this amazing control over knowing the exact sequence of events that's going to happen. We lose that with parallel programming, and that's what makes this a little tricky. So it's a lengthy explanation for me to say that's essentially why we're using a queue instead of just saying, oh, we'll just call a function and let it continue running. Well, when does it finish? We have to measure that. And so the queue is going to give us that control back by saying, I will know that this process is finished essentially like when there's something in the container. And so the queue is going to help me understand that. That's quite a lot, but we will see it in action. And in the meantime, I'm going to do the exact same thing by creating a second worker called P1. And the only thing that's going to differ here, it's still computing a sum of elements in a list. The list it's going to get is the second data slice, and it's still going to put it into the result queue. So everything else here is going to be the same. I, of course, have not written partial sum, so I should do that. This is an easy function to write. So I'm going to take the detour here to write the function partial sum, because what this function is going to take is it's going to take a data slice as input, and this data slice that I'm giving it is this initial argument here. And so it's a list of integers. And then the other thing I need to give it is the result queue. So that is of type multiprocessing dot queue with a capital Q. That's very meta. It's not going to return anything. So this is, as I was saying, this is an important part of understanding parallel programming. Previously, we had functions. Those functions returned values. It's a fundamental idea in serial programming. In this way of implementing parallel programming with multiprocessing in Python, everything is around not returning a value, but placing a value into a queue when you're finished. So if I were to write a doc string for this, I could say, what does this do? It takes as input, a list of integers and a queue, and places the sum of the list's elements into the queue. Note that it doesn't return anything, because instead of it returning a value, that value goes into the queue. And you say, well, okay, I've got a list of integers. I want to sum them. And this worker is not going to then continue subdividing the problem over, multiple different processes. It doesn't need to. The whole idea here was I'm showing you dividing it over only two workers. So that division has happened. And then the idea then is just, well, when I call this function, this is essentially a serial or sequential function. The only difference is the value goes into a queue. So all I have to do is to say that the value I care about is the sum of the data slice. Okay. In this particular case, only getting half the data. But at the end of the day, now I have a serial. This whole function is serial, and place the value into the queue instead of returning it. I'm going to say, and I have a built-in method that comes alongside the queue object called put. So I'm going to say result queue dot put my val. And that's it. That's the end of the function. So it's a lot of explanation for what ultimately is, instead of me returning the val, I'm just putting the val into the queue. And this queue is, gosh, I hope, passed by reference. So it will be able to just simply be passed into each of these processes, and I'm still going to be able to see it outside these processes. So we will hopefully, definitely, be able to see the values inside this function that are put into the queue. That having been said, there's just a little more that we have to do. Okay. I have declared the process, but Python also wants us to start the processes. So I've said what I want the workers to do, but I haven't told them to begin. So I'm going to tell the workers to begin by saying p0.start, p1.start. And now they are running. Meanwhile, my code continues. So if I were to say like, hi, what is happening is this process has begun. It's now starting. The worker is laying the mulch to help me out. Here's another worker that's also laying some mulch for me. And then I'm sitting here and I'm just going to print whatever I want. Okay. So I've subcontracted it out. But all of that is happening together. So instead of thinking, this is probably the most important way of understanding this, is that instead of thinking about this line executes, then this line executes, then this line executes, what happens is this line executes, but that means that this function is getting created and going through the process of summing these values and putting them in the queue. Probably before that finishes, and the functions that we're going to call are going to be more complicated than just 2 lines. So this function is going to start iterating and going through what might be very complicated work. In the meantime, the next line of code is going to execute, which is starting the second process. And if these processes are complicated enough, the code down here is going to execute before either of these processes are finished. So this is what I mean by saying control is gone. And you have to grasp control back over your code because you no longer know the exact order. For example, I don't know necessarily which one of these is going to be done first, right? And so I need to be able to track that. But for now, I would say, I think we're not quite finished with what we're going to do in terms of this specific example, but it's fair to say, congratulations, this is your first official parallel program, right? This is the beginning of starting processes that are running in parallel. Now, that having been said, right now the processes are both running in parallel if your computer has more than one core, right? And we know my computer has 10 cores. Your computer has more than one core. But I could, in theory, fire up an old computer that has one core on it. And the question becomes, what would happen if I start to run this code on a computer that has only one core? Good question for you. It was anticipated perfectly by Yasmin there, who said, what's the minimum number of CPUs for this, right? Do I have to have 4 cores to run this? Or if I started 18 processes, but I only have 10 cores, is that going to break Python? Let's focus on the first side of that question, though, which is, will this code run on a machine with one core? So there's a few possibilities. The chat seems to be pretty wise on this because the correct answer is there, which is that it would run. If you only have one core, will it run? Yes. What's not quite right is to think that it will then automatically become a sequential or serial program. So to say, oh, I only have one core, so that means that I'm going to ignore any parallelism and say, or any notion of starting multiple processes, I should say. And I'm going to start this, which means I don't look here yet. And I'm going to go and do this function. And then when it's finished, I'll come back here. And then I'll do this again. And then when that's finished, I'm going to come here. That's not right. So this is a critical point, that this would work on a computer that only has one core. And this is where we understand what concurrency really is. So I always ask students, when I teach at Carnegie Mellon, I say, how many classes are you taking right now? And they'll say 4 or 5, or sometimes somebody's out there enough to try and take 6 courses or something, right? And then I say, well, how can you be here now if you're taking all those courses at the same time? And the reason why is that, if we come to human language, the implication is not, if you say, how many classes are you taking right now? The implication is not meaning you're literally taking 5 courses at this exact moment in time. What it means is that you have 5 courses that are in progress at the same time. So what we're really doing here is called concurrency. What do I mean by concurrency? Concurrency means having multiple tasks in progress at the same time and managing that in some way. So I always try to give folks some examples. You could have many cups that you want to fill with water, and that's concurrent. It doesn't matter if you have 12 pitchers that you're using to fill up the water cups or 1 pitcher. If I'm putting a little bit of water in each of the cups and I'm going around, that's a concurrent process. So I don't have to have multiple workers in order for that to be concurrent. Spinning plates. I could do that with one hand. Now, I can't, because I can't spin plates. But if I could spin plates, right, I could have 10 plates spinning, and all of those plates are in progress. But at any one point in time, this hand that I'm using to spin the plates is only contacting one plate. So I only have one core, one worker. Or having multiple applications open on your computer. If you want a computational example, if your computer has 14 cores, but you have 20 applications open, does your computer crash? No. For the same reason that they made computers for many years with only one core in them, but you could have a lot of different applications open, and the reason why is concurrency. The idea that your operating system is capable of managing spinning plates, right? Because it's moving from task to task so quickly that it's able to keep them all spinning without you noticing. So that's a really important computational idea to get. And I think most people never get it. And it's conflated with parallelism, which we've already kind of defined, which says, what is parallelism? It's the concept of literally doing multiple things at once. Okay, so you could take multiple classes, I guess, literally at the same time if you had one of those time turners from Harry Potter. And I suppose that would be parallelism. But if we come back to my other examples and we think about like filling cups, if I have multiple pitchers, well, as long as pitchers are pouring out at the same time, that's parallelism, because there's multiple tasks that are literally happening simultaneously. That's another good word, simultaneously. And we could also say, well, yeah, I have 20 applications open and 10 cores. If I'm dividing those applications over the cores, that's also parallelism. If I'm spinning plates with 2 hands, or I bring in a friend and we have 4 hands spinning the plates, you have 4 cores. Those are examples of where concurrency and parallelism overlap, right? Because it's concurrent. There's multiple tasks in progress at the same time. But if you're doing those tasks with multiple workers, then that's parallel. So you can have concurrency without parallelism. For example, if I only have one worker, that's concurrency but not parallel. You can have parallelism without concurrency. That one's a little bit more complicated. We're going to delve into some pretty dark arenas towards the latter stages of our class, and I think we'll actually see an example of that, but it's well beyond what we want to do right now. In the meantime, Alistair said, I think literally at the exact same time that I did, that Hermione does take multiple classes at the same time with the time turner. So we found the right audience. That's good. That's good. That's the whole point. All right. So meanwhile, I've been talking about Harry Potter, and I've not finished our function. So the processes have been defined. The processes have been started. And meanwhile, the code continues. Okay. So I'm not going to actually print hi. What I want to do is to come back to this and say, how do I know that they've stopped? So when do I know that the workers are finished? And I can do that with another method for my processes, and it's called join. Okay. So join does something special, which is to say, where is my control? And join kind of gives us the control back. There's a little bit of a cost associated with it. And the cost is that the code will now not continue here until P0 is finished. Meaning until that value goes into the queue as at the end of my function, the join is going to do something called blocking, essentially, which is to say the next line of code will simply not get executed. This is what causes a lot of frustration, not just in Python, but in any type of, making this transition to parallel programming, is because now I have to keep this in mind, right? That I have to allow things to start in parallel and then also remember to coordinate them completing. And so I want to call join on P0, and then I also want to call join on P1. And this is not like, I want to be clear, it's not stopping the parallel programming from happening because the processes start. And meanwhile, I hit this line of code and it says, okay, well, I'll just wait for P0 to finish. And as soon as P0 is finished, then I'll call this. Then this line of code says, even if P0 is finished, I want to make sure that P1 is finished as well. And, this blocks 2. So if we ever reach here, if we ever reach this point in the function, what do we know? Well, we know that both are finished. Where are the results? They're in the queue. Okay. So if P0 and P1 are finished, I know I have two values that are sitting there waiting for me. And so let's grab them. We just need another method that's coming from the queue object. So we're going to say, vals, I guess I could say val A equals result q.get, and val B is equal to result q.get. I'm going to get both of those. And then at the end of this process, I'll say, I could return something, but this is just a little demo. I don't need to return anything. I'm just going to print the value. So we're going to print that the sum of the list elements is, and then what's the sum? It's the result of worker 1 plus the result of worker 2. And when we run this in the terminal, the sum of the list elements is 5050. So it does work, at least in theory, and for this data set. But here's a question for you. Which worker gave me this? there's two options. Did it come from worker 1 or worker 0 or worker 1? Good, the chat is wise today. It's tempting, even when you see that we call p0.join, and it says, I refuse to continue until p0 is finished. So you think, oh, well, that means that p0 has to finish first, and then p1 has to finish. No, I mean, this could take an hour. We're summing elements of a list. It's not going to take an hour unless I give it a trillion things. But this could take a long time. And this function might be very quick. So maybe I just divided it, or because of resources, for whatever reason, this worker could finish first. And so if it's finished, if P1 is finished first, the first thing into the queue is going to be its value. So this line is going to just basically pass straight over it if P1 finishes first. If P0 finishes first, then I'm going to have maybe a little bit of a wait when I see P1.join. So the answer, which is correct, is not P0. It's the first one to finish. And we didn't have to, like, they didn't have to represent the parallel program, multiprocessing didn't have to do it this way, but it's the nice intuitive way that whoever finishes first should be the first thing out of the queue. This is why it's called a queue, because if you get into a queue or a line first, that should give you priority to be the first person at the front to board the train or whatever it is we're going to do. So we've run our algorithm. We've seen that the answer is 5,050. Good. The question though is, what would we rather do? Like if I want to split the work of summing the values of a list, what would be better? Or I added a comment here for you. I think that should make it clear. If P1 isn't finished, it's going to block. If P1 is finished, it's just going to keep going. AKB wants that control back, right? You're desperate to have control. That's the nice thing about coding. It satisfies the control freaks among us. That's a good question. I want you to think about it. The hint I would give you is, well, you could always add a label to something. So think about if we have people who are in line, right? And right now they're just values that come from summing a list. You can imagine I'm putting a red sticker on one and a blue sticker on the other, and now I'm going to be able to tell them apart when they come out of the queue, right? So we just need to do the same thing in terms of what the queue is, but the queue then is going to not just have a value get put into it, it's also going to get a label. So then we can know which one came from which, but that's not really what I care about, because in this particular example, I don't care which one gave me val A. Okay, no one answered my question though, and that's all right. I'll forgive you. My question is, what would we rather do? And this is a much more general question than summing the values of a list. But if I'm splitting tasks or a task over a bunch of worker bees, right? The most natural question would be to say, well, how many worker bees do I have? And why don't we split this task into essentially equal pieces where each bee gets the same amount of honey? It's a terrible, terrible analogy, but you get my idea. And here I've split it into two pieces. And it would be a lot nicer, just a lot more elegant, so to speak, if I generalize the demo here that we have over multiple processors. So if instead I wrote a function called sum_multiprocs, and it takes, say, a list of integers as input, I'm going to call that data, and it's going to take the number of processors or processes that I want to divide this over. And I'll say what it does. So what this should do is, divides the work of summing an input list of integers over n processes. And then it returns the sum of all elements in the list. What's nice about this is that it just looks like a normal old function. It takes a collection of integers, it returns an integer, meaning its sum, but it's going to divide it over numprox. And now numprox is just a variable. What this means is, if my computer has 10 cores and yours has 14, well, I'm going to split the work over 10 cores. You're going to split it over 14, and that's going to be what's best for each of us. And we can each call some multiprox with our own custom values. So this, for example, is going to be what just goes in as a parameter to the sum multiprox function. But all I'm going to do is generalize what I've done here. So we have a collection of data, and before I divided the data into a bunch of pieces, but there were only 2 pieces before. So it was easy to divide them into equally sized pieces. Just divide them at the midpoint. The idea here is we want to divide the input data list into numprox equally sized chunks. But then there is a natural question, which is, how big should each chunk be? So you tell me, how big should each chunk be? I'll come back to this. I see there's a lot of confusion, or a little bit of confusion around the join. What really you should see when you see this is that the code cannot go here unless they're both done. So if P0 finishes first, this will happen as soon as it's finished, and then this will happen as soon as P1 is finished. That's option 1. Option 2 is P1 finishes first, in which case this becomes irrelevant because I'm going to wait until P0 is finished. And once it's finished, I'm going to call P1.join. It's going to be like, yeah, but I'm already finished. So there's no notion of blocking. So it only blocks if you have to wait. Blocking only happens if there's a wait. So all of these 2 lines together say, I'm not going to do this unless they're both finished. And that, I think, should make it easier to understand. All right, but now let me come back to, we're dividing this. So BZ gets the right idea, which is that the chunk size should just be, well, divide the length of the data divided by the number of processors. And I want an integer here, right? But we also want to be careful, right? So think about if the length of the data is like 1003 and the number of processors is equal to 10, like on my machine here, great. Then chunk size is equal to the integer division of 1003 by 10, which is just 100. When you divide that, you get 100 with a remainder of 3. Okay. But then the problem becomes that then, well, if everybody has the same chunk size, this is not going to be good. Right? Because you're going to have 100 elements for the first process, 100 for the second. You're going to have 10 processes, each get 100, and 10 times 100 is 1,000, so I'm going to be missing 3. So the great idea here is, let's just put those last 3 elements in the last chunk. If we have a big data set, we're not going to have a huge number of processors or processes. And so there's just going to be a few things at the end. So we should keep this in mind, and we will put extra elements in the final process. That's the only thing here that's harder than what we've already done. Everything else is going to be the same idea. I'm going to create slices of my data of approximately equal size. I'm going to define processes where each process is like my worker bee. I'm going to start them, and then I'm going to join them. And then at the end of that process, I'm going to grab values from the queue. I'm going to add them all together, and then that's the answer. So that idea will be the same. The first thing we'll do is make a list containing my sublists. So I'm going to define data slices to be a list of lists of integers. It's going to start off being empty. Okay. So this might look complicated. It's not. Data slices is a bunch of things. What is each thing? It's going to be a sublist of integers. I don't even need this. I could just say data slices equals brackets, but always I like to think about what's my type. And then I want to say, let's range over my number of processors. And I keep saying processor, but it's process. So I'm ranging over the workers that I have. And then I'm going to say start index is equal to I times chunk size. And the end index that I care about is equal to I plus 1 times chunk size. So if you think about this, when I is 0, this is going to be 0, and this is going to be 100 for this chunk size of 100. When this is 1, this is going to be 100, this is going to be 200, then 200 and 300. That's great. That's what I want. So these indices will be 0 to 100, 100 to 200, 200 to 300, and so forth. But we should be careful. The last one should be 900 to 1,000, and 3 for our ongoing example. So if we're in the final chunk, I'm going to say if I is equal to the number of processes minus 1, then I'm going to update the end index, and I'm just going to say go all the way to the end. So we're going to push it all the way to the end, and I'm going to say length of data. Okay, so now I know what the start index and end index is, and I say, okay, good. What's my current slice? So my current list is equal to the data, starting at the start index, going to the end index, and now it doesn't matter which chunk I'm working with because I'm handling the final chunk. I know I'm going to get all the data, and I'm going to append that to the current list. So now I've divided up the data into chunks. Great. What do we need to do? Well, we split the data into pieces. Now we should probably create our queue. So I'm going to have a result queue, and that's multiprocessing.queue. So that's just empty. Every worker is going to punch its values into the queue. Now what do we do? Well, start the work. So in this case, we want to start the work, but you're going to have numprocs total workers. So it's not just p0.start and p1.start. You're going to want to declare the workers and then start them. So what we want to do is to say, okay, processes is going to be a list of, and what we care about is multiprocessing.process. And it's going to be empty. So these are going to store our workers. And then we want to go through and declare what each worker gets access to. So for each slice in the data slices, and there's numprocs data slices, we're then going to say, all right, the current process, I'm going to call it P, is equal to multiprocessing.process. And you might remember, or not, that you have target equals the name of the function, and then the args are going to be the arguments to that function as a tuple. So remember that previously, when I did this for just 2 processes, the target was partial sum, which I already wrote. So it says, give me your sublist. I'll sum the values in it. and then I'll put it into the queue. So target's the function that I want to call, which we wrote down here. It's 2 lines long. All it does is sum the values and put them in the queue. And then the arguments are the list of things that I want to put in the queue and then the queue itself. So that once I've done that, it's the exact same thing. I can even copy this up here, right? Everything is the same because I called it result queue. The only thing that differs is, well, it's not data slices of 0. It's the current slice. It'll be useful to say, let's append that process to this list of processes that I've made. And then I want to start the work. And then I want to make sure that I join. And this will allow me to start all of these processes and make sure that they're all finished. Unfortunately, though, what I've written here has a bug. What is it? It's very subtle. And I'll give you a hint. It's not some pointless gotcha. It's something related to understanding what's happening with the parallelism. Calling join after start. We definitely want to call join after start. But I think I know what you mean. Should the joins be outside the loop? Now, why would they want to be outside the loop? Because I definitely want to do numprox joins. I want to have, every time I start a process, I want to join it. The problem is, if we understand blocking, this would block until P is done. Which means, say I've got 10 processes. I start the first one. I give it its 1/10 of the data. It starts running. That's what happens here when I start it. Good, it's working. And then in the meantime, I carry on. So it's going to start its process. I look at the next line of code, and the next line of code is p.join. So we've done all of the hard work to set up all these processes, but actually what would happen if I wrote the code like this is that I would wait until the first process is finished, and I would block here, and only then would I work with the second process. I would start it, and then I would wait on it to finish. So it's a critical way when you're working with this way of implementing parallelism. It's critical not to do this and to allow them all to start. And then after we have started them all, only then should we allow them to join. Okay, so I will have a separate loop. I'll just say for P n processes, because everybody here has numprox length, p.join. So if I have 10 different workers working on this, they're all going to start. And then what this will do is the fancy version of what we saw before. Okay, the high level version that I want you to think of, we only reach this point in the code if all processes are finished. And now we have the control back. If you want to think on a very low level, what happens if the initial process finishes before the other ones? That's fine. Well, we're going to, do this, join, and then go through and wait on the second process to finish. And when it's done, we're going to check in on the third. But that's probably the easier way of thinking about it. Like, we'll say, wait on the first one to finish. And when it's done, you say, is the second one done? So we loop back up. If it is, just keep going. If not, wait on it. And in general, for the kth process, when we go through the loop the kth time, we say, is the kth process finished at this point in time? If it is, just keep going. If not, wait. So is the kth process finished? If yes, carry on, loop again. If not, wait till it is. But at the end of the day, if you wrote a lot of code like this, you would just see this come up over and over again, that you start your processes in one loop and you end them in another, or you block for them in another. And that means that when I reach this point, I know that they're all finished. And if they're all finished, that's good news, because if they're all finished, well, this means all values are in the queue. If I can spell it. Okay. So if they're all in the queue, just get them. And now this is just a matter of saying the total sum that I care about is equal to 0. I'm going to range over the number of processes. And I'm going to say total sum plus equal to, well, go in, look at the queue, and grab a value. At the end of that process, I'm going to return total sum. Okay. This, as was the case before, is a dreaded inventory term from anybody who's taken accounting, which is FIFO, first in, first out. But I think you probably already have the intuition that the first, because it's called a queue, the first process that finishes is going to put its value into the queue, and that's going to be the first thing that we drag out. We're not trying to force these things to finish in any particular order. If we cared about, which value is associated with which worker, we would label them. In this case, we don't, because all I care about is the sum. There is a critical point here too, which is if you look at our function really doesn't have any parallelism. It does, but it pushes all of it to a subroutine. If you look at this, at our function, this looks like a serial function to me. Serial and serial and serial and serial and serial and serial, right? The work of the parallel processes kind of happens here, where you need to know a little bit about the parallelism. But even after that happens, what happens? Serial and serial and serial. So all this is just classic code, right? You just need the conceptualization of saying, well, the values are in a queue. I know this is the function that I call to go in and get something out of the queue. And when I get each thing, I add it into the sum. But this is serial code. So it's not bad practice. It's good practice. In the same way that good practice is making sure we have modular code that calls a lot of subroutines. In the same way, this is a nice reusable way of writing parallel code by saying, well, at the highest level, I have a task. I want to divide it over this number of processes, and then it's going to return something. And most of it is serial, and then there's going to be a little bit of work to parallelize this over multiple processes. If we can do this, the real question is, what should I do, right? At this point in time, I've written my sum function based on parallelism. Great. What is it that you might want to know? How long it takes. Yes, how long it takes. I probably want to be importing time. It's been a long time. I shouldn't have left you without doing some kind of timing algorithms. So let's see. I could also make sure that my code is right. I don't know. I probably should do that too. So I could say data equals list range 1 to n plus 1 and n equals 100 and numprox equals, I don't know, 8. And then I'm going to print some multiprox of data and numprox. Okay. And I probably should just run it. Okay, so it prints 5050. I was lazy. I didn't even say what I was printing, but it prints 5050. So it's working. It seems to be working reasonably quickly. Good. All that is good. And notice, I know this computer that I'm working on has 10 cores. I divided it into 8 processes. I could divide it into 16. I'm still going to get an answer. And here's where I want you to think. Just because you try to divide it into 10 pieces because you have 10 cores, that doesn't mean that what Python is going to do is say, oh, that means that I'm going to take this piece and give it to this core and this piece and give it to this core. No, you don't have control over that to that granular of a level. And that's good. You don't want that control. However, if you have 10 cores, it probably makes sense to divide it into 10 pieces. So let's produce a demo then. So let me just have a function called timing comparison. And it's just going to time a serial approach for summing elements of a list against a parallel one. That's all it's going to do. If the parallel approach is faster, then it's going to make us think does this mean that I should just have a sum multiprox function that every time we want to sum elements of a list, I'm going to call that? That actually is going to produce some weird behavior, right? If that's true, because it means to optimize things that you would want to do this all the time. So for now, let's see. So I'll say n is equal to some value. And let's set n equal to 1000. And then I'm going to say, same thing. Let's just create the values from 1 to n. And then the question is, how many processes should I use? Well, the number I have available. So here is the nice thing about this multiprocessing.cpu count function, which is that I can just say numprox is equal to it. And now I have code that's very portable. I can hand you this code and you can have a computer with 16 cores, or you get access to a supercomputer with 10,000 cores. And it doesn't matter. You're just going to access the number that are available on that machine, and that's what numprox is going to be set to. You can even run this on an old computer that only has one processor. So we're going to divide the work over the number of cores that we have available. This is what's nice about writing code in this way, because we have a function where it's a parameter, and now it's just something that I have in one line. So we're going to time the two approaches. Let's time the parallel one. So I'm going to say start parallel equals to time.time. Then I'm going to say, let's call sum multiprox. And remember, all it takes is data and the number of processes. So you see that here. Once I've called that, I don't care about the output. I just want to call the function. I'm reasonably sure it's right. I'm going to have an end parallel that stops the stopwatch. And then I'm going to have a total corresponding to subtracting the two. And then I want to do the exact same thing on serial. So I want to have something that starts the stopwatch. So I'm going to call this start serial. I'm going to call a sum function, which let's just compare it against the built-in function in Python, sum of data. I'm calling that in my partial sum. So let's make a fair apples to apples comparison. Instead of me writing another function, and we know how to write this function, you just range over all the elements in data and add each element into some variable that you declare. But let's take this for granted at this point in the course. And then I'll say n serial is equal to time.time, stop the watch. And I'll say total serial is equal to n serial minus start serial. Okay. And we could say print. I could do a fancy print statement, but maybe time taken, and then the total. And then we're going to have a print down here that says time taken and total serial. And we should say by parallel algorithm, and this is by the serial algorithm. And once we've got those two runtimes, so there's always one extra thing that we do, which is to just say how much faster is the optimized algorithm compared to the previous one. And if that's the case, then I want to make sure that I print my speed up. So I'll print it in a fancy way to say the speed up obtained by the parallel approach is whatever the total serial is divided by the total parallel. Okay. So in other words, if this takes a minute and this takes 1 second, then the parallel approach would be 60 times faster. That's something that we've seen already, but now we're ready to run. The question is, what do we think is going to happen? So for n equal 1,000, and this list of length n, remember my computer has 10 cores available. What do you think the speed up should be? Like, give me a number. Two answers here. One answer is 10, because I have 10 cores. The broader answer is the number of cores you have available. So if we run this on a computer that has 1 core, the answer would be 1. If it's on 2 cores, it would be 2. If it's 10, it's 10. If I go and run it on a supercomputer with 1,000 available to me, then the speed up should be 1,000. That's the dream. I did not call this function. So let's call the function. I'm going to get rid of this, actually, because we've already validated that. Let's just clean up what we're doing. Okay, let me try that again. Let's call the function. And this looks really exciting initially, until you realize that the time taken by the serial algorithm in seconds is 4 times 10 to the negative 6 seconds. But the parallel algorithm takes 0.14 seconds, or 0.15 seconds. So it's much, much slower. So the speed up is not good. And the question is what to do. There's kind of a couple answers here. One thing we could do is increase the size of the data. So we're going to do that. Remember what our speed up is. And we get a little better. We're not times 10 to the negative something, but things are still bad. And so then we increase the size of the data again. Let's go to 100,000 and run it again. And notice the parallel algorithm is taking about the same amount of time. Actually, it was faster this time when we multiplied the size of the data by 10. So the parallel algorithm is taking the same amount of time. The serial algorithm is getting a little bit slower. And our speed up is starting to creep upward. So if we go to 1 million, hopefully this is going to continue. Now the parallel algorithm is is taking a little bit slower, but the speed up is getting a little bit better. We were at 0.0023, and now we're at 0.0072. So if we think about, there's a graph here, right? And if you think about what's happening to the speed up over time, it's increasing as the size of the data get bigger. This is another important, like absolutely vital mental image for you to have about how parallel programming works. That as the size of data get larger, parallel algorithms speed up compared to serial will often improve, meaning there often is a point at which the parallel algorithm is better than the serial algorithm. And that's one more, maybe a little bit more subtle reason why we care about parallel algorithms in the first place, is that if you don't have a lot of data, maybe they're pointless. But we get more and more and more data. They're coming everywhere all the time, right? Meaning that algorithms that run in parallel over time might win out for these large data sets. Let's see if we can make it win out for this example. We're up to 0.036, so that is quite a bit better. And now we're at nearly a second for the parallel algorithm. And what were we here? This is 10 million, so we're going to go to 100 million. We're going to start hitting the point where I don't have enough memory to store all these integers on my computer. And I might have hit that point here. So we'll see. Now we're going to finish. The parallel algorithm now takes 10 seconds, and the serial algorithm takes 1.73 seconds. So we're at 0.036. We're getting there. We're not quite reaching the point where the parallel algorithm is better. And so kind of fortunately, every time we want to sum the elements in a list, we're not going to be writing a parallel function for this or relying on it. And the reason why is overhead. And there's kind of two things that are going on. In general, there's always going to be what's called overhead. So if I think about, I'll often have student teams who work on a project. And I've moved from allowing students to, or making students work individually, with being able to work in teams of up to 4. And I always tell them, don't anticipate that that means you're going to be able to get 4 times as much work done as if you were working individually. It's actually a great way of thinking about parallel programming, because of course, there's going to have to be coordination and communication among our 4 workers. In other words, there's going to be an overhead, some amount of fixed energy usage or time or resources or whatever that have to get consumed, and you're not going to have this perfectly efficient process. In other words, you're never going to expect a parallel algorithm if run on a computer that has n cores. If it's a true fair comparison against a serial algorithm, it's never actually going to be n times faster. You wouldn't expect that. But what you do expect is, as the size of the data grow, your speed up will get better. Hopefully it will head in the direction. But for any particular value, it's not going to be perfect. And the reason why is overhead. So this particular example suffers from, I won't be able to get us to having a speed up greater than 1 for a couple of reasons. One reason is I picked an example that's trivial. All I'm doing is summing the elements of a list. If I were doing something way more complicated and I were splitting that in 10 pieces, well, there's the hope that that overhead of introducing parallel programming would be outmatched on the other side by saying, yeah, there is a little bit of overhead, but your speed up coming from the fact that you divided this problem over 10 pieces is going to outweigh that. Overhead is always going to be an issue, though, and this is why you're generally not going to run a lot of parallel algorithms on a home computer. Things are going to be completely different if you work with a supercomputer, you work with a cluster, you work with, a very fancy NVIDIA setup that's got huge numbers of cores that you can work with. All right. But for your standard 12-core laptop, are you going to do this a lot? No, but that's not what computing is all about these days. So we're doing computing at scale. as much or more than what we're doing on local machines. That's point one. Point two is you're getting an unfair assessment of how good parallel programming is because of our old tried and true fact that Python just sometimes kind of sucks. And I mentioned at the very start of what we're doing, but the multiprocessing module in Python has huge amounts of overhead associated with it, with setting up all these processes and organizing them. And the reason why is because parallel and distributed computing was kind of bolted on to Python long after it had been introduced and people had started working with it. They were like, oh yeah, well, we need a module for this. Great. But the problem is, because it wasn't designed for parallel programming from the ground up from the beginning, it means that you wind up getting a lot more overhead than you would in a lot of other places. This is a huge part of the reason why I was proud that I think my course 10 years ago was the only programming course at the intro level that had parallel programming in it anywhere in the world. And a big part of that reason was because I taught the course in the Go programming language, which I think probably was maybe a little more popular then than it is now. But that is great for things like web servers, where you have all these tasks and you want to divide it over a bunch of servers. And the reason why is because parallel programming is built in. This demo that took me an hour and a half to run in Python or show you is like 25 minutes in Go, if that. And just doesn't require quite as much explanation and navigation of the overhead. So keep that in mind. We're working with Python. It does have support for this. It will allow us to do some really cool things, which are the things we're going to look at with something like Monte Carlo simulation, a very natural problem to parallelize. We're going to see that. And with things like working with a space, like what we've seen before with cellular automata, where I maybe divide up my space into a bunch of different sub areas, and then each area gets assigned to its own process that is in charge of that space. So we're going to see examples of both of those like paradigms as we go through this. There's going to be overhead. Python is going to annoy us. To get the speed up to go over 1 when we run our comparison, I'm going to need a big input. But we're going to win, I promise you. And unfortunately, that's what we're going to have to do next time. So I look forward to it. We're going to see some much cooler applications of parallelism in practice. Always remember that parallelism is not quite concurrency. You can maintain multiple plates spinning if you only have one hand devoted to it, if you're a good plate spinner. So you can have concurrency with no parallelism involved. But parallelism is such a way of life today that when we add this concurrent code to what we're doing, we're going to get parallelism fall out. We'll see more examples next time. I can't wait to work on them, but I will see you then. And until then.